Okay, to finish my presentation, this is just an application of in geology. I'm going to talk more. I'm a hydrogeologist and coast oceanographer. I'm going to give you two cases of the application of this equilibrium and from the uranium series for hydrological purposes. And in the first case, I will show you how we calculate groundwater discharge using excess of radon-222. It's again in this equilibrium we have much more radon in the surface water than we would expect. We'll see where it comes from. And we can use this signal to calculate groundwater inputs. And in case 2, I use radium-223 and 224, the short-lived radium isotopes, to calculate water residence time in small bays, which is important. So why do we care about groundwater fluxes in general? So one reason is that they bring a lot of chemicals to the area where groundwater discharges. So this water has been a long time in contact with the aquifer. It will dissolve all chemicals, and it should be also contaminants and naturally occurring chemicals, and they will eventually dissipate in coastal areas and lakes. And this would affect the geochemical cycles in these areas and change the ecological status. It will bring new nutrients, new chemicals. So sometimes we talk about non-point sources pollutions, where the fluxes, the groundwater fluxes are not specified in certain areas, like spring, for example, would be a point source, but they are diffusive fluxes along the whole coastline. And those nutrients that extra nutrients that the groundwater brings and pollutants can cause eutrophication. And it's a big problem these days because we put a lot of fertilizers through agriculture on land, and this could cause algae blooms and other processes. And the other thing why we want to determine groundwater is because we started using groundwater more intensively and overpump and create so-called maybe voids in the subsurface. And in coastal areas, salt water will fill these voids and we'll have salt water intrusion that will contaminate our drinking water resources. So for the typical water resource applications, we want to know how much. How do we measure groundwater seepages? There are different ways. I listed only 4 of them. One of them is seepage meters. These are authentic chambers, physical measuring flow. And the other way is geochemical tracers. So we use the disequilibrium of radon and radium in the surface water to calculate groundwater discharge. Groundwater is very highly enriched in this because it's been so long in contact with the aquifer. It accumulates all these radioisotopes, while surface water doesn't have the source, so we would expect to have very low concentration. So if we see some signal of these isotopes in surface water, that means that they must be source, and it's most likely groundwater. Now also people do flow modeling, groundwater modeling based on water mass balance, Darcy's equations, and so on. And they use some geophysical approaches. They take thermal images and look at the temperature differences and some other techniques. So I'm going to show you an example of measuring groundwater discharge along the coastline of Florida and a few lakes in central Florida. And I don't know if you're familiar, but when the first Europeans came to Florida, Ponce de Leon, he was looking for the fountain of youth. So there was some tale that somebody was telling him that there is this magic water that keeps you young forever. In fact, if you go today to St. Augustine, which is in central Florida, you will find a fountain of youth. There is this spring there that historically people believe this is the one that he was looking for. Remember I was talking to you about hormesis at the beginning of my talk, and people inflate and drink this radon-enriched water. Groundwater is radon-enriched water, and spring water is radon-enriched water. So most probably they knew about the hormesis effect way before we knew about it. So if you look at Florida, map of Florida, these are dots with monitored offshore springs. Closer and further offshore springs, fresh water coming out in the ocean. Sometimes they're very close to the shore, you can walk and see them, and sometimes they are just even miles away from offshore. And people made an attempt to measure radon concentrations. So this is the locations of the springs listed here. And this is a map of Florida with this contour diagram showing the concentration of radon in these areas. And you can see that highest concentrations of radon in the surface water was detected exactly at the areas where we have the springs. So this is how people came to the idea that they can calculate this flow of springs using radon concentrations. Right? So part of my research is to study some of those springs. Actually, those springs are located right here, ones that I'm going to show you next slide data. It's a spring area which has 13 springs. They're very close, 100 meters from land. And it's marine environment, and you see the boil of fresh water coming out from the ocean floor. And so part of my research is to study the discharge of these springs. And so most of the springs are located in this area here. My tour is not working, it's right here. And so this is a salinity. We put on a boat instrument that measures salinity continuously, nothing fancy. And then our radon instrument, this box of RAD7 that measures continuously radon with the gas chamber. And we measured salinity and radon, and you can see that they are mirror images. In areas that we see low salinity, fresh water, we see very high radon. And the ranges are very high. Offshore, we see about 2 becquerels per square meter. This is becquerels per cubic meter multiplied by the depth. So that we will look at inventories only. So 2 orders of magnitude differences from the area where the springs are to offshore. And salinity again from 6 ppt up to 32 ppt. But I'm going to show you today the principle. How do we use this radon? So we detected it. So what can we do about to calculate how much water comes out, not only where it comes out. So usually when we do this research, we first do these surveys. We detect where those sources are, and then we use the same instrument and we put it in a station and we measure continuously radon in this place to calculate how much freshwater groundwater is coming up. So I will show you an simple example from lakes. They work exactly the same. We have very high concentration of radon in groundwater and very low concentrations in surface water. And so if we see somewhere here close the shore high radon, that we assume that there is a discharge, groundwater discharge in this area that contributes. And this radon is in excess because it's delivered by groundwater, it's orphan. It's more than it can be produced from the dissolved radium in the surface water. So usually they do that using Darcy's law, and usually groundwater, this is an example of water table near shore in the lake, and water flows naturally from high topographic gradients to low topographic gradients. In case of radon, as I said, we're going to have in this water, groundwater, a lot of radon because this water has been for a long time underground where the source is, and it's very enriched in radon. And I'm talking about orders of magnitudes, 3 orders of magnitude higher concentrations. than in surface water. Remember, this radium comes from radium-226, and radium-226 is part of the composition of the ground, of the aquifer. And the advantage of this method here is that this signal will dissipate through the whole lake, and if we have even a non-homogeneous distribution of the seepage, it integrates over the whole lake. At the end of the day, we want to know how much in total groundwater is coming to the lake, which is the advantage. And so how do we do this mathematically? So imagine the lake is this box. So in order to calculate the discharge, we need to figure out how much excess of radium only coming from groundwater is going to the water column. But there are other sources of radium to the water column too. So one source would be groundwater, which sits with certain flux centimeters per day or whatever flux. And then we have some radium, which is part of the composition of the aquifer that will produce, and radium is a gas, and it will diffuse and you get to the water column as well. So we need to account this is not coming from groundwater, and if we use it, we will overestimate our seepage, right? So we need to take out this process. And then the other thing that we need to account is that radium is a gas, and it will be gas from the water column. And the solubility of gas depends on temperature, so we need to know also the temperature of the water. So we construct this mass balance where we have sources coming from groundwater, fluxes coming from groundwater, from diffusion. We also have some radium dissolved in the water that will produce, so radium production. We have to account for this one too. And then we have to account, these sources are balanced by atmospheric evasion and radioactive decay because it's a radioactive gas. Okay? In small lakes, this is very simple because they're shallow, they're very well mixed. So we go there and measure the total radium. And we also can measure diffusion by taking some sediments in the lab and analyzing through gamma spectrometry how much radium we have there, and we can calculate how much would be from diffusion. We can also collect radium from surface water with our this manganese fiber resin, or we also use some fibers. I'll show you some example. So we can evaluate all these sources, diffusion, production. We can calculate even the loss because we know the temperature solubility. The temperature depends on solubility. We know the decay constant, so we can calculate this parameter too. And the only one unknown in this equation would remain the flux coming from groundwater. And the rate of this delivery will tell us about the rate of groundwater inputs. Make sense? So if you want to know a little bit more about this method, we published it in this paper. And so this is the main method, the main approach, how we calculate groundwater seepage. We go there and we measure, we deploy our system and measure total radium inventory. Again, it's concentration multiplied by depth. And then we account for all the sources and sinks, and by the missing part, we calculate the discharge, or how much radium is delivered only from groundwater. And this is radium flux. So at the end of the day, we want to know this centimeters per day. So we divide this flux by the radium concentration in groundwater, or our radium groundwater N number, and then we get centimeters per day of the water seepage. All these equations here are very detailed, described in this paper, and I'm more than willing to talk to you about this. The last case that I will present is using the short-lived isotopes of radium-224 and radium-223. They're coming from the two different chains of thorium-232 and uranium-230. So in this case, this is a river system, and this study picture is from the Yangtze River estuary in China, where I participated in a project with some Chinese colleagues. The method was developed by Billy Moore in 2000, and it actually calculates water residence time in an estuary. So imagine we have river coming to an estuary, enter the ocean, and so what it calculates is the water age of the water, the water age in this bay. How old is this water in the bay? And what we do, we calculate, we use the ratio of these two isotopes and measure these two isotopes in the river, the ratio in the river and the ratio in surface water. And we can express from this equation the time, and we can calculate age of water. Or this is the time when the river entered the bay. So to make it more clear, and so to do this, we use this the Lake coincidence counter. I can talk to you about this method. We collect large volumes of water, and this is a large variation of the small column that I showed you in drinking water. In this case, it's filled with this fiber, which is covered with manganese dioxide, which absorbs radium. Then we put it in this instrument, and we measure the radium 223 and 224. And so this is sampling points along the estuary. The numbers here is time, or this is the time when the water left the mouth of the river. And you can, by looking at these numbers, you can actually follow the pathway and the current and the mixing of these river masses. So you can see that we have 0 ages exactly at the mouth of the river when it leaves the source. And then the moment it leaves the source, it becomes orphaned and starts decaying, and then eventually lower concentrations offshore and higher ages of water offshore. We also published this paper. I don't have the references, but the original method is well known and it's been applied to many different places around the world. So it's why do we are interested in this residence time? Especially biologists are very interested in looking at this residence times in terms of different element recycling and vitrification processes, and they follow currents through these methods and things like that. In the paper, we also performed, we had a team, they did numerical modeling where they simulated particle tracking. They tracked particles dropped at the mouth of the river and looked at the distribution based on current knowledge on currents, and they reproduced the same pattern as the radium isotopes. In summary, hoping that I'm not boring you, I hope that I have showed you that the radium and the radium isotopes are very useful tools to study both geological and hydrological processes in coastal environment and also in freshwater systems. For my dissertation, I worked on lakes in central Florida and the method was found very useful. For 2 years, we screened 7 lakes. We did seasonal study in 3 of them, which is quite impressive. We know that, and it's an invasive technique. You don't go and drill wells there. You basically deploy your system, measure it for some time, perform the mass balance, collect some sediment in the lab, perform the diffusion and mass balance, and calculate discharge, which the local authorities found it very attractive, and eventually they would implement this for regular monitoring technique.